Okay, so whenever you want to interact, you can stop me, or you can post your clarification in the chat box too. Okay. So have you got my slide?
Yes, sir.
Yes, sir.
Okay, thank you. Is it okay?
Sir, we're seeing the presenter view.
Are you seeing the presenter view or
Yeah,
not? It's okay, or want to see?
it's fine, sir.
It's
Is it
fine.
okay?
Yes, yes, it's fine.
Okay, okay, thanks. So we can start with the introduction to design. Okay, so we all know that design is a creative activity. Okay, and also some people feel that it is a rewarding activity or a satisfactory activity. Okay, so design is a general terminology which can be applicable to all type of disciplines, irrespective of engineering or arts or science or whatever may be. So this is a very general term. So it's more on creativity and rewarding and very satisfactory job. Okay. So in general, this design process or this design involves so many steps. So it is completely iterative in nature. Okay, it is an iterative procedure. Okay. So why we have to go for design? It may be this is for a specific need. Okay, so we have to propose different ideas, or we have to synthesize ideas to achieve the proposed need or objective, specific objective, whatever may be. Okay, so here you should know what is need and what is want. Okay, so need is the minimum requirement that is to be a must for the customers. Okay, so wants means we have to add some more values, okay, to the design, so that can be a wants. Okay, so we have to define the objective very clearly. Okay, sometimes the objective may be ill-defined. Okay. So over different processes, we have to tune this objective to the well-defined one from ill-defined one. Okay, so to achieve this specific purpose or specific objective, we have to identify, or we have to synthesize the ideas to achieve this. Okay, we have to synthesize the ideas. We have to list out the ideas that for the desired objective. Okay, once it is being done, for example, in the case of a chemical process, or it may be a product, or it may be a equipment. Okay, whatever may be. Okay, particular stage in the production process, whatever may be. So we have to design these things. So product means for example this vaccine, co-vaccine. Okay, vaccination for COVID. Okay, so such a cases. So this is our objective. So first is we have to see whether we have the existing process, or we should develop a new process. Okay, or we should make some modification in the existing process. Okay, so the product is the objective. Then we have to find out the ways to achieve this product. Okay. Then, as I said, the manufacturing process, we have to look what are all the methods, manufacturing processes that's listed out in the literature, and we have to analyze it. Okay, to get the best process design. Okay, or once you finalize the process design, Okay, we all know that process is series of operations. Okay, so for a particular operation also we have to design a particular stage of the process also we have. So design, as I said, design process is an iterative process. So the very first step in the design process is that we have to define the objective, okay, or the purpose, or you can say specifications, whatever may be. Okay, so we have to define it. It should be a clear statement. Okay, so it should be a clear statement. So whether it is need or want, that also we have to define. Okay, so once the objective is defined, because some cases what will happen, for example, the marketing team predicts we need 30 percentage more product than existing volume. Okay, so they will propose we have to expand the process plant. Okay, that is objective. Okay, now we have to look upon different possibilities. Okay, whether we should expand the plant 10 percentage, because over the period next 2 years they are anticipating that the product demand will shoot up to 30 percentage than now. Okay, so such a cases we should the team, the design team should sit and they have to analyze whether this has to be expanded 10 percentage or 20 percentage or 30 percentage. Okay, so what would be the capital cost, what would be the operating cost. Okay, so whether do we have any competitors for this product. Okay, so we should do so many analysis. Okay, so or because it is anticipated in the next 2 years, so we don't know what will happen in the next 2 years. Okay, so whether the product available in the outside, okay, so whether we can purchase it, whether the qualification or a specification of those product or quality of the product or meeting our requirements, those things we have to think of. Okay, we have to think about these things, and we have to find out a solution. Okay, then only we, because capital investment is more for 20 percentage or 30 percentage. Okay, and 10 percentage means it's modest, or we should go for a new process than existing one. So everything has to be analyzed. Okay, so we have to collect the data details of the process. Okay, so we have to collect the data, physical properties, design methods, chemical process, size of the process. Okay, so what is the demand. Okay, marketing survey also you should do marketing demand. Okay, then how the growth of the plant. Okay, so everything, then you have to assemble all the data for the process, equipment, property. Okay, so selection different types of equipments. Okay, so nowadays we people are talking about sustainability, intensification, those things, how many things we are talking. Okay, so sustainability is the one major thing required nowadays, because last 3 decades lot of research are going on in intensification. Okay, so around from 1990 or 1980s. Okay, so a lot of intensification methods like micro reactor, or you can say high gravity separation process, then reactive reaction plus separation, those things, integration of these things. Okay, so many things are going. So the even you can see this methyl acetate process proposed by Eastman Chemicals. Okay, so it has very complex in nature with respect to separation. They have the azeotropes, so many things. Okay, so they have conventional, when compared the conventional process, it's like it has around 28 unit operations. Okay, then they do this intensification, then they integrate all the reaction, separation, the like azeotropic reactive extraction or reactive distillation, those things. Then they integrate, the plant becomes the plant has only 3 units. Okay, So like that, this process intensification minimize the size of the plant. That is also one important thing. That is the very first definition came out from the researchers for process intensification. This is a process intensification is very old technique. It is established in 16th century by a metallurgist for separation of gold from gold ore. So that is completely green energy based integrated plant, because they used water wheel and this water wheel is connected with your reactors or crushing, grinding, everything through proper gear arrangements. Okay, so I think you might have studied in process intensification course. Okay, Agricola is the author who published his paper on Metallica library journal. Okay, about these things. Okay, so apart from miniaturization of the plant, we have to talk about safety, then waste minimization. Okay, then we have to talk about economics, so many things. Okay, so we have to collect all the data that is required for this development of new process or modification of the process or identification of a new stage or a design of a particular stage and equipments. Okay, and the other auxiliaries data, property data like chemical properties, physical properties, everything we have to collect and we have to arrange, order them in proper manner. Okay, so from these data, we have to find out the possible or general generation of possible designs. Okay, so we have to eliminate, because here so in this case, once you collect the data, because our objective may be a clear statement or ill-defined statement. Okay. So if it is ill-defined statements, we need so many things. We have to do high-level meetings, or we can do some simple calculations. From this, we can modify or we can tune our ill-defined objective to the well-defined objective. Okay, so then collect the data, then from the data analysis we can identify the ways to meet the objectives. Okay, so we have to generate the possible designs for our objective. Okay, so here you can do the complete work, what are all the things that has to be. Here we have to analyze, we have to subject the identified design methods to two different factors, or you can call constraints. Okay, internal constraints and external constraints. When you subject the possible design methods to these internal and external constraints, we can narrow down the number of possible designs. So what is constraints? So which limit the ideas, or which limits the methods that is being proposed to achieve the objective. Okay, here we have two different type of constraints. One is external constraint, another one is internal constraint. These external constraints are shown here using thick lines. Okay, these thick lines are representing the external constraints. So the external constraints are resources, physical laws, standards and codes, government controls, economic constraints, and safety regulations. Okay, so these are all external constraints. When we the listed out ideas are subjected to these external constraints, because the external constraints normally very rigid in nature. Okay, they are fixed constraints. It's not in the hand of a design engineer. Okay, so we have to filter out our possible design methods using these external constraints. Okay, physical laws means it has to, we have to validate the process using material balance, energy balance, or you can say mesh equation. What is mesh equation? Anyone knows what is mesh equation? Anybody knows?
Sir, mass, energy, enthalpy, and entropy. Is that true? Is that correct?
No, no, no. Mass, energy, enthalpy are same. This means
Oh,
this is a material balance, this is equilibrium, this is summation. Summation means sigma x equal to sigma y equal to 1. This is enthalpy. This is energy balance. Okay. So that is called mesh equation. So this is material balance, or you can say mass balance. This is energy balance, or you can say enthalpy balance. Here you can, this is S represents summation, that is sigma x equal to sigma y equal to 1. That is, you might have studied in distillation column, design or separation process. Here equilibrium, that is y is function of x. Okay, so normally this is being used in the process also, or even particular separation also we can use. So that is physical laws, or you can apply thermodynamics. Okay, all the things we have to apply in physical laws. Resource means availability of resources. Again, the sustainability comes here. So we should not sacrifice the future generation for our present demands. Okay, that's the main objective of this sustainability. So resource whether it is raw material resource or energy, we are talking about availability of gas for next 15 years, 20 years, 30 years. So we have so many reasons. So coal will be available for longer period, but this crude and natural gas will be available for very short period of time. So we are in the urge to develop some alternative energy resources like solar energy, then bioenergy, biorefinery concepts, those things. And also safety regulations. This is another external constraint. Safety regulations means nowadays or even last 20, 30 years, or this you might have studied in safety, so many accidents like in Bhopal case, or even 2, 3 years back on a ship spilled out so much of oils over the surface of water. Okay, so that is another. So we have to talk about, we have to focus on this safety regulations of the process or equipment operation, those things. So with respect to process, it has to generate minimum waste. Okay, so it should not spoil aquatic or land or air. Okay, whatever may be. Okay, so we have to minimize the harmful hazardous chemicals in the atmosphere. Okay, by using suitable treatment methods. Okay, so safety regulations proposed by the government or these government controls, we should obey these things. Okay, then economic constraints. Your process would be the economically viable one. Okay, so you should see the raw material cost and also product cost. If the difference is more, okay, then you can say the process, the capital operating cost or capital cost of the plant is more. Okay, so we have to see the gap between your raw material cost and product cost, or your product quality, whether it is a bulk chemical or fine chemical or specialty chemicals, whatever may be. So we will see in later slides what are these things. Okay. So after filtering out the proposed or listed out the design things, using these external constraints, you will get the possible designs. Okay, once we go these possible designs, then we have to find out this best design using these internal constraints. So here internal constraints, we have 6 things. One is a choice of process conditions, materials, personnel, time, and methods. Okay, so these are all called internal constraints. Internal constraint is very less rigid in nature, and it's, or we can call it as a variable constraint. This is in the hand of design engineer. Okay, so we can the design engineer can control all these things. So choice of process, you can see, for example, sodium hydroxide manufacturing process. You may have different process, alkali process or mercury process, electrolytic process, those things. So you can select based on these things. Okay, the choice of the process you have to go select. Okay, even this crude oil distillation, you may have a atmospheric distillation unit, vacuum distillation unit, those things. So again, you have different choices for these things. Then process conditions. We have to define the process condition. As I said, ADU and VDU, the conditions are different. Okay, so the materials again matters, whether it is a cylinder to be heat exchanger, whether which fluids would be taken in which side, cell side or tube side. So this is based on the type of materials, or whether it is corrosive in nature or fouling in nature. Okay, whether it is reactive. So we have to see so many things. Okay, so after seeing these materials, you can select whether it is a copper tube or a alloy tube or aluminum tube, okay, or a mild steel, so many things. Okay. Then personnel means the manpower, how much manpower is required. Okay, that also we have to look in. Then time. What is the time required to reach the product to the market? For example, Bharat Biotech announced that this Covaxin will reach the market. To reach the market, the Covaxin will take around 120 days. Bharat Biotech said they need 120 days to reach the product, the market. Okay, so if you want now, it has to be started at least 4 months before. So the time, how long it will reach, how long it will take to reach the market, then methods. Okay, so we have to once the possible designs are arrived based on these external constraints, we have to subject these designs to the internal constraints. Okay, all these 6 are applicable to the filtered out design methods. Okay, then we have to go for the final design. So here you can select and evaluate the possible or feasible and probable designs subjected to different constraints, fixed constraints and variable constraints. Okay, so once it is being done, or if you want to go back, you can do this. That's why it's called iterative process. Again, you can redo, you can reanalyze these things, and you can get the final design, best design. That would be the final, which satisfy all the things. The very first thing is profitability, economics. Then you have to see the sustainability. Okay. Then you have to see whether operating cost or capital cost, size of the plant. Because sometimes what will happen, because the process is once you define the process conditions here, what I said. Okay. So normally we cannot run the plant at steady state. Okay, you need to shut down the plant, emergency shutdown, start up the plant. Okay, you have to start up. So those times the plant would be in unsteady state conditions. Okay, so lot of uncertainties will be there, because we all know that the composition of the feed, then mass flow rate of the feed, then pressure temperature conditions, those things we know. Okay. Then the final output is the product, so we should know the product flow rate, composition, temperature, pressure conditions. Okay, so you can simulate it, or practically you can identify. So when you measure it, what will happen? The process condition is highly, the process conditions will vary from the defined values. Okay. So such a cases we cannot go for the exact design. Okay. So we have to provide some contingency, or you can say we have to apply some factor of safety to this. Okay. So we have to apply the factor of DC to this. Okay. So our equipment should not be over designed one, and also if you consider 10% or 15%, okay, that variation is normally will be there in the process plants. Okay, so the equipment has to be designed properly. Okay. So it should be over designed. For example, in the case of distillation column, when you design a column number of stages using McCabe-Thiele method or Ponson-Savarit method, okay, so we'll get the number of stages. Then you have to you will that will give the ideal or theoretical stages. then applying the efficiency of the column or tray, you can get the total number of stages required. And also this efficiency is the average efficiency. Normally it will change tray to tray. Okay, because your feed is somewhere between or exactly located above and located between the stripping section and enriching section. Okay, so the feed quality we will not get continuously in the same range. Okay, it has some range. The value of the or the quality of the feed varies continuously, and it will reflect on the performance of the equipment. So we should provide some contingency, or we have to over design by applying factor of safety. Okay, so those things we have to do. Okay, again, if you do well, you give more than 30-40%, such cases your equipment size will be bigger one than the required one. So automatically it increases the capital cost. So if the size is big, automatically your operating cost also will be more. Okay, so initial stages in when the process are developed, the big is best, the concept is followed. Okay, big is best. So the process plant will be the bigger one. Okay, the over the period what happens now because of this process intensification, people are talking about this miniaturization of this process plants. They want to go for very small plants in order to minimize the utility cost, raw material usage, and they are talking about different principles of process intensification like intramolecular interactions, okay, and optimizing the driving force or maximizing the interfacial area, and they talk about the one of the principle like synergism between the integrating the operations. Okay, sometimes every molecules should experience should have same history in the equipment or process. So these are the principles. Then they apply this to different approaches called spatial domain, structure, energy domain, synergy domain, okay, and temporal domain. All these things. Okay. So many things are there. So we have to obtain this final design. So the design should be a very optimal one, optimized one. It should not be over designed or it should not be under designed. Okay. So we have, and also sometimes what happened, the instrumentation, whatever we are using to measure the temperature, pressure, flow rate, composition, those things, that the accuracy of these instruments will also reflect on your design calculations. Okay, these are all some other constraints other than this. Okay, so once your final design is being decided based on these constraints, internal, external constraints, okay, we can go. We have to go for product design or process design or equipment. Okay, so we all know that chemical process, that is a transformation of raw materials into the said chemical products. This is the general definition for a chemical process, because our demand or our objective is fixed, that is the product. Okay, how we are arriving this product using from the resources or feed streams. Okay. So we have different unit operations here. Okay, we have to identify the unit operations, because the chemical process is nothing but transformation of raw materials into desired chemical products. Okay, so normally this chemical process is a two-step process. This means that first we have to identify the requirements, the unit operations required to achieve the target from the source. Okay, so here you may have mixing, you may have reaction, you may have separation units. We need purification units. Okay, we need pumps, we need compressors. Okay, so condensers, heat exchangers, okay, e-boilers, evaporators. You might have studied so much of unit operations in your earlier semesters, particulate separation technology, separators, okay, thickeners, okay, then drums separating vessels, okay, high pressure vessels, low pressure vessels, so many things. In chemical technology, you might have studied how these operations are interconnected. Okay, so we have to identify the process, operations required for to get these product streams. Then the second step is that we have to arrange them in a proper manner. Okay, so your feed is preheated reactor. Okay, so this reactor we have the separator unit. Okay, like that it goes on. So we have to arrange them in proper manner. Okay, that is the two-step process. Okay, so here if you know, if you see the process, this general very general equation is feed streams are converted into product streams. This is the general equation. Okay. So we have the general anatomy of this chemical manufacturing process is like this. Okay. So the reaction is the heart of the process. Here you have feed, here you have product. This is the simplest one. So you have feed and the feed is entering. So you may neglect this also. Okay. So raw material is sent to the reactor. After reaction, you get the product. Okay, it may be a complete conversion or incomplete conversion. Okay, so such a cases you have to separate the product from other things. This unreacted feed, and you have to get the product, and you will get waste, and finally you will get the product also. So one of the intensification objective is that we have to minimize the byproducts, we have to minimize the waste, and we have to increase the conversion with the safety and economics. That's another motivation for this process intensification. Okay, those things we will study in intensification. Okay. So reaction, if required, you have to go for, you have to add this stage 2, that is feed preparation stage. Okay. So this feed preparation, raw material is converted, subjected to feed preparation, because your feed has to enter the reactor at a particular temperature, pressure conditions. Then you should do some homework, or you have to prepare your feed or make your feed to eligible to enter this reactor. Okay, using this thing. Preheater, you may use preheater, or you may use you can use the communication equipments to reduce the size in metallurgical industries. Okay, so for example, in the case of bauxite aluminum process, or you can say Bayes process, that is well known process. It's a cyclic process. So here you have a bauxite. So this bauxite is a combination of different things. Not only it not only has Al2O3, it may have SiO2, Fu2O3, moisture, so many things. Okay, so the composition of the bauxite is highly complex. Okay, so you have a Al2O3, that is the required one. Si silica, then Fe2O3, you may have other mud, sand particles, then moisture also. Okay, and what you should do, you have to minimize the size of these things using crushing, because from the mines you will get in terms of feeds, or in terms of higher inches, then it has to be a size reduction should be used. Size reduction equipment should be used to reduce the size of the particles, to increase the surface area, to extract the Al2O3. Okay, so this is like then you have to go for crushing, then you have to go for grinding. Okay, so crushing, grinding, then the size is decreased. Okay, so then here you can use different types of crushing or grinding, wet grinding or dry grinding, those things. So here itself you will add NaOH. So bauxite plus NaOH, that is the main reaction in the Bayes process. So finally what will you get? So then after having some minimal residence of time, then it has to send to the digester or reactor vessels. Here only the complete reaction takes place. So you have to maintain the process condition in the digester. You have to have a series of digester in the process plants. The temperature would be around 120 or 125 degrees centigrade. It has to be operated at a pressure of 6 to 8 atmospheric pressure. You have 4 different long, tall digesters. It is digested properly with NaOH. Here also you have to add NaOH. So this NaOH added in two different places. One is for wet grinding, another one is for digestion. So during digestion, what happened? This NaOH react with our Al2O3, SiO2. So you will get sodium aluminate and sodium silicate. This sodium aluminate is the required one. So you have to go for this product separation. So here you have the product. This product will have Al2O3, SiO2, sodium aluminate, sodium silicate. That is very dangerous one because normally it is very sticky in nature. It's like gel type. So if the process conditions are altered, what will happen? It will clog the pipelines. Okay. So very first step in the separation process is that we have to remove the sodium silicate. Okay. So once what will happen? The digester is operated at very high pressure temperature conditions. First, it has to be sent to the separators. Okay. So here your flashing, or you can say flash drums. So your vapor and the liquid streams are separated here. So the liquid streams, once separated, it goes to desilication tanks where the sodium silicates are removed. Once the silicates are removed, it has to send to the thickeners, or you can say clarifiers, where we have Fe2O3. Normally this Fe2O3 will not react with this NaOH. So this sodium, after removing the sodium silicate in the desilication tanks, then it goes to the clarifiers where Fe2O3 is removed. So we have series of product separations. Okay. So once you remove the solid particles Fe2O3, okay, then it is sent to the thickeners where the clarifier, you will get the clear liquid at the top of thickeners. So here water is being used as a solvent. So again, water is the majorly consumed in metallurgical process industries. So the sodium aluminate is cleaned by the water, so it is diluted. Okay, normally this sodium aluminate and water will go in countercurrent manner. Okay, so finally you will get this sodium aluminate. Then it has to send to the filters to remove the fine particles like sodium Fe2O3, those things. Then it is after filtration, you will get the clear saturated sodium aluminate liquid. Then it is sent to the crystallizers where the sodium aluminate is you have to maintain the temperature to achieve the supersaturation. Once supersaturation is the driving force for crystallization. Once supersaturation is achieved, what will happen? You by proper agitation mechanism, you can by maintaining the temperature, you will get the Al2O3 particles, crystallization of Al2O3. So the sodium aluminate is again dissociated like Al2O3 and NaOH. So this Al2O3 is again separated, then this diluted NaOH is again sent to the evaporators once it is being concentrated against. That's why it's called cyclic process. So you have bauxite plus NaOH, you will get sodium aluminate. So the sodium aluminate is again, once you separated Al2O3, this NaOH is concentrated, again sent back to process. So this is a cyclic process, by a cyclic process. So if you see this process, you can see why do we need feed preparation or product separation. So if you know the product details, or if you know the conversion of your reactor, or what are all the possible byproducts, waste or conversion, those things, you can decide how many separation units you can go. So product separation, then once it is being separated, if the quality of the product is product meet out the specification, okay, then you can stop here. Or still, if you want to increase the quality of the product, we have to go for this product purification stage. Then finally send to the storage, then finally reach the market. So this is the general anatomy of the process. This is general anatomy of the process. So normally this is very conventional in nature. So it is expressed using this onion model. Okay, so onion model of process design is called like this. This is conventional one. It's layer by layer process. That's why it's called onion model. Here you have a reactor, that is the heart of the process, as I said. Then followed by you have a separation and recycle system. This is separation, and you have a recycle system. Your raw material is recycled, your byproduct is taken out. Okay, sometimes it may be recycled here also. The recycle system, then heat recovery system that comes. These are all additional things that comes to minimize the cost of the product in terms of operating cost. Okay, heat recovery system. For example, this case in a bauxite process, after a digester, we have a very tall column. We have a very tall or big vessels, pressure vessels for because here what happens, digester is operated at around 5 to 6 atmospheric pressure. When the output of this final column output reaches the column, what happens, the big startling process taken place, you have vapor and hot liquid. Okay, so this vapor is maybe reused, or this hot liquid may be used to preheat the sodium hydroxide. Okay, so this sodium hydroxide is being used in autoclave and also in the because in wet grinding process. So in wet grinding, normally the temperature has to be of sodium hydroxide would be around 60 to 65 degrees centigrade. So you have to preheat this. So you can use the heat available or heat coming out from this pressure vessels. Okay, or you can say flash drums that can be used. So here the heat recovery system is essential so that we can minimize the utility requirements, so that your operating cost will come down because of these things. Okay, so once you recover the waste heat available from the process streams, okay, automatically we can minimize the utility requirements, whether it's a cooling utility or heating utility. The heating utility normally will be hot water or steam, or you can say thermic fluids, okay, Dow chemicals, or okay, Dow thermia, different things are there. Then you can go hot flue gases, or you can use electrical heater. Okay, sometimes you can use molten metals. Okay, the hot oils normally it is used around 250 degrees centigrade. If it is up to 180 degrees centigrade, you can use steam as the heating utility. Okay, so the cooling utility means it's ambient water, normal water, or you can go for cooled water or chilled water, or molten salts, aqueous organics, refrigerants. So based on the requirement, you can go you can select your utilities. Okay, we will see those things in selection of utilities in the while discussing about design of heat transfer equipments. Okay, so once these utilities are once you have an analysis of all these things, then we have to think about this water and effluent treatment. Okay, so this is the final layer of your onion model for the process design. So this is called like this. Okay, so this is the general anatomy of the chemical manufacturing process that you might have studied. So the design of this process is as I said, we have to consider all the constraints, whatever we discussed, like internal constraints and external constraints. Okay, this is about process. Then we move to the product. So product means we have three different types of products. One is bulk chemical, another one is fine chemical, or you can say pharmaceuticals or specialty chemicals. That is another terminology that is being used. Okay. So the major difference, or sometimes what will happen, you cannot differentiate whether it is a bulk chemical or fine chemical. Okay, so it is like arbitrary. This classification is arbitrary, but this is a general classification with respect to products. Okay, with respect to products. So here, if the quantity of chemical produced is in the order of magnitude 10 power 4 to 10 power 6 tons per year, then you can say they are bulk chemicals. Okay, and also since they are produced bulk, the cost of the product also will be in the lower side, but it doesn't have any value added. Okay, so the quality or additional value of the product will be very low. Okay. Mostly these type of bulk chemicals are produced in continuous process plants. Okay. The plants are mainly dedicated plants. Okay, so we cannot use these plants for some other purpose. That's not the case in other fine chemicals and pharmaceutical chemicals. Okay. So as it's dedicated plants, the flexibility of these plants is very low. So it is normally this bulk plants structure is irreducible structure, very rigid in nature. Okay, so it doesn't have any flexibility. Okay. So the safety and environmental efforts are relatively low. So this is a general characteristic of bulk chemical process plants. Okay. Fine chemicals means, for example, solvent, dimethyl. Solvents, you can use acetic acid. Okay, so these are all things are called fine chemicals. Okay, so the order of magnitude will be around 10 power 2 to 10 power 4 tons per year, and the price will be in higher side. It has some better value. Okay, both these bulk chemicals or fine chemicals are identified based on its purity, composition, those things. So again, because sometimes it is undifferentiated. Okay, so most of these fine chemicals are produced in batch wise. So since they are batch wise, the columns or the plant can be operated for multi-purpose. Okay, so batch wise means if you have 2 or 3, 4 reaction vessels, you will operate 1 or 2 at a time. Other 2 can be standby or it can be used for some other purpose. Okay, so if the process in the plant itself, if you have 2 different processes, you can operate, you can use those vessels for the other required purpose also. So the utility of equipments is more in the case of batch process batch plants. Okay, so the flexibility is high as it has a multi-purpose, and safety and environmental efforts are normally high in these fine chemicals. Okay, the purity also high with respect to fine chemicals. The specialty chemicals normally produce low volumes. The cost also more. So what happens? The cost is more means what happened? The value is more. Okay, so it is produced in less quantity, but it has more product value, product rate. Okay, so the value is added value, additional value is very high. These type of specialty chemical plants operated batch wise. Again, it is multi-purpose plants and highly flexible plants and relatively having high safety and environmental efforts. Okay, this is general classification. So if you have any doubts at this point, you can stop me, you can ask. Otherwise, I can go to next slide.
Sir, here what is added value based on what we explain the added value?
Added value means specific purpose. So, for example, Al2O3, no? Al2O3 you can sell as it is. But if you want to go for Al2O3, normally will be in solid form. So that is a bulk chemical. Okay. So if you want to reduce the size of the Al2O3, then you have to go for another size reduction equipment. Okay, so then added value means the Al2O3 obtained from a crystallizer. If you do the particle size analysis, it would be in the wide range. So if you want the product between 10 micrometer to 30 micrometer, then what happens? Then you have to do some sieve analysis, or you have to go for some other grinding. Okay, so such a cases is additional, no, value added. That would be the reason. Or for example, sulfuric acid, you may have 95%, 97.5%, 99.9%. Most of the chemicals, it has a purity and also the composition. That's the thing.
So added value is effective, proper and effective analysis, right, for the product form. Okay.
So additional value, that's all. So additional value of it.
Okay.
So we can continue our discussion next class. again, this we can start with this products. Okay, so today we have discussed what is
And another
design.
thing, sir, can you explain it like this, sir? Because we cannot see the diagram properly, and so that the flow charts also inside.
Didn't get them properly.
Cannot see. Now we can see it, sir, in the PPT form.
Previously, you could not see that.
I don't know about others, but for me, it's like.
What happened?
Sir, it is quite. It will be small, sir, but not totally invisible.
Oh, the sizes are small.
Yes, sir.
So using
Even
presenter view, so the pop-up was
I
very
showed the
small.
presentation view. I don't know why it is so.
Now it's
Yes,
fine,
so
sir.
this is
Now
better.
it's fine, sir.
Slideshow view is better. Yeah.
No, I used this only. I don't know why it is so.
Okay, okay.
This is okay.
Now
No. So it's coming again back in the small form.
Oh, this one.
now this is
Yeah.
Oh, okay. Sorry. So whatever we discussed about introduction to design. Okay. Then how the design? What is the design process? Okay. What are the steps in the design process? Then it is iterative process. We have objective, then data collection, then identify the possible designs, and we have to select and evaluate for a final design. Okay. Here we have discussed two different type of constraints, like internal constraints and external constraints. So external constraints are also called rigid constraints or fixed constraints. Then after doing analysis of the process for external subject to external constraints, we will get the possible designs. And then these possible designs are subjected to these internal constraints, which are in the hand of a design engineer. So after analyzing, we will get the best design. Okay. So then we talked about what is a chemical process. Then it is a two-step process where identification of unit operations and arranging the unit operations in a manner, proper manner. These are all the two steps in the chemical process. Then the general anatomy of the chemical manufacturing process we discussed using an example of biocyclic process for manufacturing of L2O3. So this conventional process is also expressed in terms of onion model. This conventional one. Now, if you integrate this reaction product, they are all because this is sequential one and operation based thing. So these conventional processes are arranged in sequential manner and operation based. But nowadays, this intensified process plants are task oriented. Okay, so you can integrated one. Okay, that's the difference between in the process intensified plants and these things. Okay, then we talk about different products. So next class we will see about the life cycle of different types of products. Then we move to optimization of a process plants using this onion diagram. What is the general anatomy? How it is modified for different cases. Once you change the reactor, what happens? You modify the separation, what happens? Those things we will discuss in the next class. So I stop at this point. I'm sorry, I don't know, I missed it. Okay. So next class onwards, I display the slides in proper manner. So anything else you want to share? Any comments? Can I stop at this point?
Okay, sir.
Thank you all. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.